Tamam. Şu an ekranı görebiliyor musunuz arkadaşlar? Hoş bir yazı yazayım da siyah gözükmesin.
Evet, görebiliyoruz hocam imlecinizde.
Tamamdır, süper. All right, so today we are going to talk about a new subject, which is called the root locus, okay? Let me try to write down as root locus. And in this topic, what we're interested in is, again, the closed loop transfer function of a feedback system. So what we would like to do to inspect the closed poles and their locations. So given a standard feedback loop as follows, this is our standard feedback loop with the G of S on the forward gain and the H of S on the feedback gain over here. And as you already know by heart, our closed loop transfer function is equal to G of S divided by 1 plus G of S H of S. And as you already know, this is called the characteristic polynomial. Okay. And if you find the roots of 1 plus G of S, H of S equals 0, that will give you the closed loop poles, right? And this is called the characteristic equation. If you equate the characteristic polynomial to 0. Okay. And what is the condition on stability for the closed loop poles? We heavily worked on it with the Rath-Hurwitz methods. What is the condition? So all closed loop poles should have real parts that is less than 0, right? Okay, so in the root locus, what we're interested in is that what happens if we change a single parameters of the systems, what happens to the closed loop pole locations. So that's our main concern in the root locus. So for the time being, let's assume that, so let's assume that the open loop transfer function, our open loop transfer function be equal to, what is the open loop transfer function, by the way? That is equal to G of S times H of S, right? That is the open, so you multiply the gains in this loop, G of S times H of S. Assume that it is equal to K times N of S divided by D of S, okay? Then what I would like to find out is that what happens to the closed poles. I mean, 1 plus G of S, H of S. I mean, what is the root? What happens to the roots of 1 plus? I will use another color for K so that you can see that as a parameter. So, okay. K times N of S divided by D of S equals to 0. And what I would like to find out is that what are the pole locations if K is a free parameter that I can change, let's say from 0 to infinity, okay? A free parameter or a design parameter we can change. And then we will try to find the closed loop pole locations and see what their location when as K changes from 0 to infinity. And then you can, for example, specify a specific K value such that your pole locations are closed loop pole locations are at the desired point to satisfy certain properties for such as the maximum overshoot, settling time, etc. Okay. I will show you one example so it will be more clear. So suppose we have the following feedback loop. So we have a proportional controller K over here in this example. And our plant has the transfer function s times s plus 2, sorry. And we have unit feedback. Something like that, okay? And what we would like to do is to find the closed poles. Find the closed loop poles as K changes from 0 to infinity. Change from 0 to infinity. Okay. So what is our closed loop transfer function? So our open loop transfer function is equal to K over the multiplication of these two, K over S times S plus 2, right? So it will be simply equal to K times S plus 2 divided by 1 plus K over S times S plus 2, right? And that is equal to simply K over S times S plus 2 plus K, which is equal to K over S squared plus 2S plus K. Okay. So this is our characteristic polynomial, right? So now this is my characteristic polynomial. And the closed poles are found by equating the characteristic polynomial to 0 and finding its roots, right? So let's try to find the roots of this characteristic polynomial. So this is S, by the way. Sorry for that. Now it looks like it's 25. So let me try to fix it. Okay, slightly better. Okay, let's try to find the closed poles by finding the roots of the denominator over here. And what are the root locations? So S1 and 2 in this case is equal to -2 plus minus square root of 4 minus 4k divided by 2. And that is simply equal to -1 plus minus square root of 1 minus k. Okay, so we managed to find the closed loop pole location. So we have the open loop pole locations, which was 0 and -2. But as we change k from 0 to infinity, the closed loop poles becomes the solution to this equation, this polynomial, roots of this polynomial. And for different k values, the closed loop poles get different values. And I can sketch these pole locations as well. So let me try to do that. Oh, I can put a slide over here for better view. Okay, so let's have a look at, so what are the pole locations when k is equal to 1? So, sorry, when k is equal to 0, so when k is equal to 0, we have the pole locations as -1 plus -1, right? So that will be simply equal to, one of the poles will be equal to 0 over here. I can show it by a yellow color, okay? And the other pole is going to be equal to +1, is going to be -2, right? -1, -2, and -1 plus 1 is going to be 0. And so I can also write once again that we are changing k from 0 to infinity, okay? So what's going to happen when I increase k further, okay? So this is -2. So when I increase k further, these two poles are going to get closer and closer, right? So they're going to get a -1 plus minus another value, and that value is going to be smaller and smaller until k reaches the value 1 over there, right? So these two pole locations are going to get closer and closer when I'm increasing k from 0 to 1, okay? So, and when k is equal to 1, and we have double roots at s is equal to -1, right? So these two roots are going to meet over here at point -1. So for k is equal to 1, I will have double roots over there. And if I increase k further, so for k greater than 1, the root locations are going to be simply equal to complex roots, okay? So it's going to be plus minus j squared of k minus 1, right? So the real part of the roots, when increase k further from 1 to infinity, the real parts of the roots are going to stay the same. It's going to be at -1, but the complex part is going to increase, increase, and increase, right? So it's going to be something like that. I will have, let me try to plot it something like this. Okay. So the poles are going to move on this line and that line, right? And they will go until the infinity. Okay. Do you have any questions? Okay, so if not, let's continue. So root locus is the trajectory followed by the closed loop poles when I'm changing a single parameter. In this case, it was the proportional controller gain k over there. The location of the closed loop poles changes, right, for each value of k. And the trajectory followed by these closed loop poles is called the root locus. Okay. So maybe I can try to write it down. So root locus is the trajectory followed by root locations when a single parameter is changed continuously. So what is that single parameter in our example? That is k, right? In this example. And the trajectory followed by the closed loop poles is that those yellow lines over here. Okay. So how did so this was easy when the degree, the denominator was of a second degree polynomial, right? So I can find exactly the pole locations. So, but for higher order systems, it will be difficult to plot such trajectories. They will be more complicated, but it is possible to plot them approximately, and by inspecting the solution of the roots of the denominator.
Hocam,
Buyurun.
ve sıfırdan mı başlaması lazım bu değişim şeyin?
Bir daha söyleyin neyin?
Bu değişim hani single parametre şey değişiyor ya.
Şimdilik sıfırdan sonsuz aldık. So for the time being we assume that k is a positive number changing from 0 to infinity. So you can also derive similar things for negative numbers as well. But for the time being and in our whole course, we will assume that k is a positive number.
Peki, teşekkürler.
Very good question. Thank you. Okay, so how do we find these pole locations? We simply inspected the denominator of the closed loop transfer function. So I equate 1 plus g of s h of s to 0. Okay, so let me try to write that down as with a blue pen. So 1 plus g of s h of s is equals to 0. And that simply implies that g of s h of s is equals to -1. Okay. And what we would like to do is that, first of all, we will assume that the open loop transfer function g of s h of s is equal to k times n of s over d of s. Okay, so assume that this is equal to k times n of s over d of s. Okay, so what we are trying to find is to, let me write it down, same color, like to find 1 plus k times n of s over d of s is equal to 0. Okay, and when I'm solving this equation in the complex plane, I will use two conditions which are called the magnitude condition and the angle condition. So let me try to write that down. So I can write this for, let's say, k times n of s over d of s is equal to -1. And I can write that as a magnitude. From this equation, I will have two conditions that needs to be satisfied. So magnitude of k times n of s over d of s should be equal to 1. For the left-hand side to be equal to right-hand side of this equation. And the angle of k times n of s over d of s should be equal to angle of -1. And angle of -1 is equal to pi plus minus k times 2 pi. Okay. For k is equal to 0, plus minus 1, plus minus 2, etc. Okay. So when I'm solving a complex equation, from every equation I get two conditions. Okay, so this is called the magnitude condition. Okay. Magnitude condition. And this is called the angle condition. Okay. And similarly, I can write the same thing for g of s, h of s, right? So I can write that from here. Magnitude of g of s, h of s is equal to 1. And the angle of g of s, h of s is equal to pi plus minus k times 2 pi. Do you have any questions? Then let's see one example of solving these complex equations. Okay, yes, please.
Bir soru soracaktım. Bu açı kondisyonu nereden geliyor acaba? Onu ben kaçırmış olabilirim.
So what I try to do is that now we are trying to solve a equation of complex variables, right? And we are in the complex domain. It will show up immediately in an example, but let me show you that. So in order to satisfy both sides of these equation, I should have the magnitude of the both sides should be equal to each other, and the angle of both sides should be equal to each other, right? So the angle of the left-hand side should be equal to the angle of the point -1, right? And that the angle of -1 vector is equal to pi. So in the complex domain, -1 is here, so then the angle of -1 is this pi, right? I mean, you can write -1 as like r times e to the j theta, right? And that is indeed equal to 1 times e to the power j pi. right? The angle of -1 is equal to pi in the complex numbers. Okay, maybe I will show you a simple example, and that will be more evident. Okay, so let's try to solve one complex equation by simply trying to find s cube is equal to 1. Okay, so let's try to find the roots of this equation. So as s is a complex number, I can write s as r times e to the power j theta. Okay. And in order to find the s's that satisfy this equation, I need to satisfy two conditions. So one of them is that the magnitude of s cube should be equal to magnitude of 1, which is equal to 1, right? And that is the magnitude condition. And maybe I can write it down as well. So from there, I can say that magnitude of s is equal to 1. And from there, I can say that r is equal to 1. How about the angle? And the angle of s cube should be equal to the angle of positive real number 1 over here, which has the angle 0 times k times 2 pi for k values 0, plus minus 1, etc. Okay. And what is the angle of s cube? If s is equal to r times e to the power j theta, it's 3 theta, right? And 3 theta should be equal to a multiple of 2 pi. K times 2 pi, k starting from 0. Okay, so maybe you can tell me these angles. So what is theta 1? K is equal to 0. That is equal to 0, right? And what is theta 2 when k is equal to 1? That is equal to 2 pi over 3. And what is theta 3 when k is equal to -1? It is minus 2 pi over 3. And notice that the corresponding pole locations are like then s is equal to r times e to the power j theta and r is equal to 1. Then s1 is simply equal to e to the power j theta 1. Okay, and s2 is equal to e to the power j theta 2. And s3 is equal to, oh, sorry, s3 is equal to e to the power j theta 3. So let me try to show those guys on the S-plane. So suppose this is the S-plane, okay? So this is the real axis, this is the imaginary axis. Okay? And I would like to plot my first root over here is e to the power j0, so it is equal to 1, right? So here is 1, there's 1 pole. And the other root is equal to 8 e to the power j 2 pi over 3. So it is something somewhere over there. And the other one is e to the power minus j 2 pi over 3. So it's somewhere over there, okay? So, and they are on the unit circle here, okay? And these are my solution to these equations. So we were able to find the 3 roots of s cube is equal to 1. Those complex numbers are there. And similarly, so what I'm interested in is that like g of s, h of s equal to -1. Okay, so let's do this very similar exercise by finding the roots of s cube is equal to -1. Okay, so once again, so I will get two equations from magnitude condition and the angle condition. And again, the magnitude of s cube should be equal to magnitude of -1, which is equal to 1. And from there, magnitude of s is equal to 1. And I can say r is equal to 1 once again. Okay. And let's write down the angle condition. So angle of S cube, which is equal to 3 theta. This time it will be, what is the angle of -1? So as we said minutes ago for one of your friends asked. So that is equal to pi, right? So it should be an odd multiple of pi for k is equal to 0, plus minus 1, plus minus 2, etc. So in that case, let's write down theta 1, theta 2, and theta 3. So when k is equal to 0, what is theta 1? It is pi over 3, right? And when k is equal to 1, what is theta 1, theta 2? It's simply equal to pi, right? So when k is equal to -1, what is theta 3? Is equal to minus pi over 3, right? So once again, I can plot the S-plane and show these root locations. So here again, S1 is equal to e to j theta 1, S2 is equal to a to g theta 2, etc. And so if I plot the unit circle once again, this is 1. Now the pole locations are, the root locations are, one of them is equal to pi over 3 over here. Another one is minus pi over 3 over there. And the other one is pi, like this. So these are the roots of the equation S cube is equal to -1. So that's how we treat the complex equations. So once again, if we go back to our original problem, we have 1 plus g of s,
Hocam?
h of s is equal to 0. And from there, g of s, h of s is equal to -1. Okay.
Hocam?
Yes, please. Hı hı.
3 tane kökü olduğu için mi 3 theta dedik? Ben
Evet,
direkt
diğerleri de, evet, 3 kökünü bulmaya çalışıyoruz. 3. dereceden bir denklem. So if we are given a third order polynomial at the third order equation, we have 3 roots and we found all of them. Okay.
Anladım hocam. Teşekkür ederim.
Very good. So if you would like to solve the g of s, h of s equal to -1 to find the closed loop pole locations, okay, then I need to apply the magnitude condition. G of s, h of s should be equal to 1, and the angle condition g of s, h of s should be equal to 2k plus 1 times pi. Okay. So magnitude condition and angle condition. And we assume that, let me write it down maybe explicitly, we assume that,
Hocam,
one second please, we assume that g of our open loop transfer function is in the form of k times n of s divided by d of s. Let me indicate it by k times let us have m zeros, okay? So s minus z1, s minus z2, and s minus zm. And let us have n poles in the open loop transfer function, s minus p1, s minus p2, until s minus pn. Okay, so if I can write those explicitly, these are the open loop zeros, and these are the open loop poles, right? And for the magnitude condition, I need to compute the magnitude of this guy and equate it to 1. So let me do that down below. So from the magnitude condition, I should have k times I from 1 to n magnitude of s minus zi divided by let's say I from 1 to n magnitude of s minus pi should be equal to 1. Okay. And from the angle condition, so this once again, this is the magnitude condition. And from the angle condition, I should have summation I from 1 to m angle of s minus zi. So, and I subtract the angle of the poles down below. Summation I from 1 to m angle of s minus pi should be equal to 2k plus 1 and odd multiple of pi. Okay. K is equal to 0 plus minus 1 plus minus 2, etc. And someone was asking a question. I can answer now. Angle condition.
Hocam, I was going to ask about this angle condition. How do you get 2k plus 1 times p?
So this is I'm computing the angle of this minus 3. So one of your friends asked already. So we are trying to g of s h of s is equal to minus 1, right? So what is the angle of minus 1 vector in the s-plane? Huh?
It's p.
Yeah, exactly. So it's the odd number of pi, 3 pi, 5 pi, 7 pi, etc. Right? So,
Okay.
So that simply says that, nothing more than that. Okay. And so now we were able to write down these conditions in terms of the open loop poles and open loop zeros, right? And let me show you one example. So let g of s be equal to the blue pen. So let's our open loop transfer function be equal to simply equal to k times s minus z1. And let's say s minus p1, s minus p2 times s minus p3. Okay. And suppose these pole locations are somewhere over here. So let this be the S-plane. And suppose, get the pink color over here. Suppose the 0 is there. Let's say this is Z1. Okay. Suppose this is P1. And let P2 and P3 be like complex conjugate poles. Okay. So let this be P2 and let this be P3. Okay. And how to apply these magnitude and angle conditions, I would like to show you. So suppose I do have a test point, let's say over here, okay, somewhere over here. And what I would like to find out is that if this point can be included in the root locus. So if I go back to our first example where we were able to find the closed pole locations exactly, I'm asking the question, for example, can this point be on our root locus? Can this point be on our root locus? Or can this point be on our root locus? So the answer to the first two questions is no, but the answer to the third question is yes. So for some k values, that point might be on our root locus, okay? But for the other two, for whichever k value you pick from 0 to infinity, you cannot bring the closed pole locations to those points, okay, to those test points. Okay. So let's say, and this is because and I should say that this is because all points here and there satisfies the magnitude and angle conditions for some k value, for some positive k value. Okay. So let me show that if we go back to our example. So let this S be our test point, okay? And what I would like to have is that find the magnitude of S minus that one vector and divide it by the multiplication of the S minus P1 vector, the magnitude of S minus P2 vector, etc. So anyway, maybe I can show you this, right? So what are these S minus that one vector? So like this, okay. So this vector is my, if I get a test point, so the tip of this line is, let be equal to our test point S, okay? And these vectors are all S minus that 1.4, any point I choose for that one over here. So this is the, let me again, once again, choose our test point here. Let's say S, okay, is over here. So this is the S minus that 1 point. So I would like to look at the magnitude of this vector, angle of this vector, etc. And these vectors are, for example, S minus P2 vectors, okay? And I can pick any test point and try to inspect if that is on the root locus or not, okay? So if I'm given this specific test point over here, so what I will do is that I will inspect these vectors S minus Z1, S minus P1, P2, and P3. So let me plot all of them. Okay, so this is, I will pick another S point because this coincides with those two. So let me try to pick another S point a little bit over here. Okay. So let this be our test point S. And this is the S minus that one vector. This is S minus P1 vector. This is S minus P2 vector. And this is S minus P3 vector. Okay. And the angle of these vectors are, I can say that, for example, this is theta 1. Okay. So let's say this is theta 2. And the angle of that vector is equal to theta 3. And I will call the S minus that one vector's angle as, let's say, psi 1. Okay. And if I just give some names to those points, that I will call this A point, this B point, let this be C point, let this be D point, and let that point be the E point. Okay. So now I can write the magnitude condition, this condition over here, simply as, so I should have K times the magnitude of S minus Z1. So this is AB, okay. K times AB. I have only 1 0, so I am done with the numerator here. Now I'm going to the denominator over here, divided by the multiplication of magnitude of each of these vectors over here. So I will start from P1, the magnitude of the length of AE times the magnitude of S minus P2, that vector over here, magnitude of AD, and the length of magnitude of AC over here, S minus P3. AC should be equal to 1. Okay. I just write this magnitude condition for this specific example, for this given example. Okay. How about the angle condition? So angle condition simply says that the angle of sum of zeros the difference between the angle of sum of zeros and the angle of sum of poles should be equal to a multiple of pi, an odd multiple of pi. Okay, so it will simply say that the angle of s minus z1 is equal to psi 1. Okay, and minus angle of s minus p1 is equal to theta 1, angle of s minus p2 is equal to theta 2, and angle of s minus p3 is equal to theta 3, and that should be equal to 2k plus 1 times pi, an odd multiple of pi. This is the magnitude condition and the angle condition. Do you have any questions? So what I would like to do is that once again, so I would like to emphasize one thing. Why is this question critical? So why am I all of a sudden interested in if a test point is included in the root locus or not? So can you imagine any application this might be critical? So if we go back to our very first example, so we have our plant over here and we are using a proportional controller over there, okay? So, and you will change your proportional controller gain from 0 to infinity, which is a very practical problem. That's what you do most of the times, okay? And one might ask you, for example, can you achieve a certain settling time or a certain overshoot value by changing this k value from 0 to infinity for this plant, okay? So can you achieve, for example, some settling time which corresponds to the pole locations over here by changing the k values from 0 to infinity? So for this example, so remember that the settling time was equal to 3 over psi omega m. This real part of the poles, dominant poles were determining the settling time, right? And for example, you cannot get anything better than this 3 over minus 1, 3 over 1, 3 seconds for this example. When you change from k from 0 to infinity, the best you can get is this line, but you cannot bring your poles to here. So they will be close to your imaginary axis, but they cannot get very much far away from the imaginary axis. The real parts cannot be too far away by simply changing that k value from 0 to infinity. Okay, so it will be critical to ask, for example, can you bring your poles to here, let's say, or there, let's say, or there, let's say. And for all these candidates that I drove outside that yellow line, it's not possible by a proportional controller, okay? But for the very last example, for some k value, I can bring one of the poles to this location, okay? So that's why the magnitude and angle condition are critical. Okay. And in the next lecture, since I see that the time is up, so in the next lecture, we will continue with an example and write down the rules of plotting the root locus, the trajectory that is followed by the closed loop poles when a single parameter of the system is changed continuously. Okay, so we will do that. So we will do what we did for that second order system. We're going to do that for higher order and more complex systems. Okay. Do you have any questions? Okay, so if not, I can...
Hocam ben bir şey sorabilir miyim?
Yes, please.
Notlarımı yükledim dediniz ya.
We will come to the lecture related, the course related questions later. Any questions about today's lecture? Okay, so maybe I can stop recording now. Second, please. If I can stop recording. Yes.